Basic organic chemistry class, we'll be looking at benzene and aromaticity. We're going to look at introduction, aromaticity, nomenclature, which is naming, sources of benzene, reactions of benzene, effects of substituents in benzene, and addition reactions in benzene. Benzene is the simplest member of group of cyclic compounds known as aromatic hydrocarbons. Hydrocarbons meaning contains only hydrogen and carbon. The word aromatic is from a Greek word which means pleasant smell, aroma. But not all pleasant smelling compounds are aromatic. Like esters are pleasant smelling, but esters are not aromatic. The structure of benzene is cyclohexagonal, which is conjugated. So benzene is a cyclohexagonal compound with conjugation. The formula of benzene is C6H6. When compared with other hydrocarbons, which are alkane, alkene, and alkyne, it validates that benzene is unsaturated. But benzene does not undergo the usual addition reaction typical of unsaturated compounds like alkane and alkynes, because benzene does not dechlorize potassium permanganate, which alkane and alkyne can do. Benzene cannot react with hydrogen except in the presence of catalysts, while other unsaturated compounds can undergo halogenation without a catalyst. Benzene undergoes substitution reaction and not addition reaction typical of other unsaturated hydrocarbons. Benzene does not have isomers like other hydrocarbons that have structural isomerism. In benzene, all the carbon atoms are equivalent because the bonds are equivalent. The bonds can resonate. The bonds can be delocalized, making all the carbon atoms to be equivalent. The unusual special kind of unsaturation in benzene is evident. According to August Kekule, that talk about that benzene is a cyclic structure which contains a resonance hybrid of two structures. So benzene, according to Kekule, is a resonance hybrid of two structures, or called canonical structures. Remember, canonical structures are also another name for resonance structures. This hybrid is a combo of the two canonical structures. That's why it's represented by 0 at the center, meaning that the bonds can interchange position. So these electrons are delocalizable. They can move around. In benzene, these double bonds are not existing. They are not real. That's why benzene cannot undergo addition reaction typical of other unsaturated hydrocarbons. And because this single bond and double bond are always alternating, that's why, like I said in the previous slide, the carbon atoms are equivalent. And there is existence of only one disubstituted isomer. So either it is auto, para, or meta, as we're going to see in upcoming slides. The carbon-carbon bond length in benzene are equal, and the hybrid structure is more stable than the contributing resonance structure or canonical structures, because in hybrid, the positive center is being dispersed around the ring, so that's why it is more stable. While in a canonical structure, you're going to see this positive center in one part of the ring at a time. Stability of benzene and non-existence of this free double bond makes it impossible for benzene to undergo the usual addition reaction. Rather, it undergoes substitution type of reaction. Benzene, because benzene resists any reaction that is going to destroy its aromatic nature. Because if benzene undergoes usual addition reaction, it ceases to benzene, it becomes cyclohexane. So because benzene wants to retain its nature and name, it avoids reactions such as addition reaction that can its nature. Looking at the modern orbital theory, molecular orbital structure of benzene, we can understand that benzene contains carbon and hydrogen that are on the same plane, which means they are planar, and the bonds are sp2 hybridized, meaning like alkane, they are sp2 hybridized carbon involved in benzene ring. Because of their sp2 hybridized, the bond angle is 120 degrees. In terms of the bonding of carbon, like I said, in benzene, they are sp2. But bonding between carbon and carbon is sp2-sp2 because it's the two carbon that connected to the bond is sp2-sp2. But bonding between carbon and hydrogen is sp2s because the hybridization for hydrogen is s, while the hybridization for carbon is sp2. So bonding between carbon and hydrogen is hybridization between bond of carbon and hydrogen is sp2s, while the hybridization between carbon and carbon bonding is sp2sp2. So the atom itself is sp2. The bond is talking about the two atoms that is connected by the bond is going to have the hybridization. That's why we're having sp2sp2 for carbon-carbon bonding hybridization. But for carbon, the hybridization in carbon as an atom is sp2, but the bonding is the atoms that are made up of that bond. I hope that's clear. The aromatic character of benzene, or for a compound to be aromatic, the compound have to perform the following properties. The aromatic compound must be cyclic, they must be flat or planar, they must be conjugated, meaning they must contain the localizable pi electrons, and they must obey 4n plus 2 pi electrons, which is called Huckel rule. So any compound that misses any of this character cannot be termed aromatic. So for a compound to be aromatic, these 4 characters must be fulfilled by that compound. This is explained in the following example. Benzene, naphthalene, and anthracene. The simplest of aromatic compound is benzene. So when there are 2 benzene rings, we're going to form naphthalene. 3 benzene ring forms anthracene. By following Huckel's rule, N is 1 for benzene, giving it 6 pi electron, putting in that equation of 4n plus 2 pi electron. For naphthalene, 10, anthracene, 14. So when we get the 6 pi electron, we compare with the pi electron in the ring. If it correlates, we can say that Huckel rule is being obeyed, meaning that the compound is aromatic. So for benzene, the 6 pi electron correlates because we have 3 bonds and each bond contains 2 pi electrons. So for naphthalene, we have 10 pi electrons, meaning 5 bonds. And for anthracene, so it means that these 3 compounds obey Huckel's rule of aromaticity. They are conjugated, they are planar, meaning, and they are cyclic, so they are all aromatic compounds. The compounds on this slide, you realize that structure 1 is not aromatic because the first ring has an isolated section where there are 2 single bonds that are not conjugated. Second compound confirmed consistent conjugation, validating that it is aromatic. Ring 3 confirm that the second ring by my left and the third ring have isolated form, so which means they are not aromatic. IV confirm that the first ring is isolated, so not aromatic. while the fifth ring confirms that the second and the third ring are not conjugated, they are isolated, meaning that only structure 2 is aromatic. The properties of aromaticity. Every aromatic compound cannot undergo oxidation, so they cannot react with permanganate. They cannot undergo addition reaction, but they must undergo substitution type of reaction. Thermally, they are stable. This is evident because the heat of hydrogenation and combustion is usually less than that expected. When a compound is stable, the heat liberated is going to be lesser. When a compound is less stable, it generates more heat. That's what happens when you're not with your temper, you're unstable and it generates so much heat. But when you're calm, you're very stable and you can generate little or no heat. Finally, obedience of Hooke's rule of 4n plus 2 pi electron. In nomenclature, we're talking about naming. Benzene can be monosubstituted. In that case, only one hydrogen is being replaced by an atom. Phenyl is when benzene loses one hydrogen, and phenyl is an alkyl, which means it's going to be a carbocation. Benzene can also be disubstituted, meaning that 2 hydrogen atom has been replaced. In di substitution, we have 3 isomers. We have ortho, meta, and para. In benzene ring, position 1 and 2 is equivalent to position 1 and 6. Position 1 and 3 is equivalent to position 1 and 5. So that's why we have only 1 and 2, 1 and 3, and 1 and 4. Because by my right is 1 and 2, 1 and 3, 1 and 4. If I go by my left, it's also 1 and 2, 1 and 3, and 1 and 4. So that's why we have only ortho, meta, and para in disubstituted benzene isomer. When benzene can also be tri-substituted, in that case, I have to use the number to indicate where these substituents are attached on the ring. So, and I have to follow the route so that to obtain the lowest possible combination of numbers. Now, looking at the structures below, we realize we have nitro compounds in 3 positions on this benzene ring. Position 1 is 146. This number 2 is 124. 146 and 124 are the same compound because remember the previous slide, we said that position 6 and 2 are similar. So if the one that is on position 6 by clockwise naming, I would rather go anti-clockwise to give it position 2. So the one in position 2, I will maintain the clockwise. So whenever you want to name, follow the route that is going to give this substituent the lowest possible combination of numbers. Now, when phenyl, which is benzene that loses one hydrogen, when there is addition of any atoms or group of atoms to replace this hydrogen that is lost from benzene to form phenyl, is going to give a different functionality in benzene family. It means that we're going to form another family, another compound entirely, as shown in the table. Looking at the table is evidence that alkyl, when alkyl is being replaced with this hydrogen, we're going to form alkyl benzene, which is called arenes. And when it's halogen, we're going to have halobenzene, which is called aryl halide. Aryl is another name for phenyl. So when we have amino, we are going to form aniline or aryl amine. When it is hydroxy functional group, we are going to form phenol or hydroxybenzene. Phenol and aniline, since they have a compound family name, is much more preferable when you're doing your nomenclature. When it's aldehyde functional group, we are going to have aromatic aldehyde, and when it is ketone functional group, we are going to have aromatic ketone. When it is carboxyl functional group, we are going to have benzoic acid, and when it is nitro group, we are going to form nitrobenzene. So this atom or group of atoms have given this phenyl another functionality, it makes it translate it to another family entirely of benzene derivative. This benzene is being obtained from coal and petroleum as their major source. In coal, it is obtained by distillation of coal tar. Petroleum, it is obtained by catalytic reforming. Physical properties of benzene confirm that benzene is a liquid, and not just liquid, it's colorless liquid. Because it's a liquid, it boils at a very high temperature. Melting, meaning that this liquid is not just very light. It's a liquid that have a consistency, so it can still melt before boiling. The melting point is 5.5. It has a characteristic aromatic odor. That's why it's called aromatic hydrocarbon. And because it's hydrocarbon, it is oily, it cannot mix with water, meaning it has less density. It floats on water. Water is under. That's why I said it's less denser than water. This benzene is a very important solvent that is used in the laboratory and also chemical industry. Because it's unsaturated system, we can validate its unsaturated nature using flame tests. In the laboratory, when an unknown compound is given and you want to validate whether it's unsaturated or whether it's benzene, doing unsaturated tests, we are going to use flame. So spatula, a sample is put on spatula, and the blue part of flame, this spatula is going to be heated on the blue section on the flame. If it comes out with sooty flame, it's validated that this compound is unsaturated. Remember, this is going to be the same for alkene, alkyne, as well as benzene. The reactions of benzene, because benzene is electron rich because of unsaturation, it means that it's only electron deficient reagent or species that can attack it, because electron rich cannot go with electron rich. They are going to repel themselves. So it's only electron deficient. That is why we talk about electrophilic reagent attacking benzene. That's why benzene undergoes electrophilic aromatic substitution. So that's why that's the typical reaction of benzene. Benzene has a kind of stability due to resonance energy. And because of that, addition reaction will destroy the aromatic nature of benzene. And because benzene is not less stable, benzene cannot react without a catalyst or heat, unlike other unsaturated compounds that don't need catalyst. They can need reagent, not catalyst. Under severe condition, benzene can be hydrogenated. And if benzene is hydrogenated, it ceases to be benzene. The aromatic character will be destroyed. That's why benzene. So benzene does not react with bromine with tetrachloride, unlike alkene and alkyne. Rather, and benzene cannot react in cold or hot permanganate, which is typical of oxidation because of its aromatic nature. So when doing under halogenation, benzene needs a catalyst to undergo halogenation, and the catalyst is directly related to the kind of halogenation involved. If the halogenation is chlorination, my catalyst will be iron 3 chloride. If it's bromination, as shown on the slide, it will be iron 3 bromide. So you don't use bromination and you use iron 3 chloride as a catalyst. No, your catalyst must correspond to the halogenation reaction in progress. In that halogenation, is only one hydrogen that is being replaced with the halogen. Other ones are going to go as a byproduct with the hydrogen that was substituted in the reaction. The mechanism of benzene or reactions of benzene is called electrophilic aromatic substitution reaction. Electrophilic. The three words are important. It must be electrophilic because benzene is electron rich, so we need electrophilic species, which are positive center. It must be aromatic because it occurs in a benzene ring. And it must be substitution because the aromatic nature, the double bond, the saturated, unsaturated system must not be tampered. So we are just replacing, we are not adding. So some of the reactions of benzene are nitration, sulfonation, halogenation. Friedel-Crafts reactions are two. In Friedel-Crafts, we have acylation and acylation. Generally, in mechanism, the first step is a slow step which involves attack on the electrophile on benzene ring. Then before ionization. So what is the mechanism behind this attack is what is shown on this slide. When an electrophile is attacking benzene ring is meant to create a space for it to bond, and is going to give it a nucleophilic center, which is a carbanionic center. In that case, remember the slide on bond cleavage. So the bond is going to cleave in the direction to generate carbanion. That's why it's going to move in the arrow of the electrophilic species. When it does that, it's going to deposit negative, that is carbanion and carbanionic center, where this electrophilic species is going to bond. When it bonds, behind it is a carbocationic center. Then this arrow, this movement will continue in the manner to neutralize this generated carbocationic center by creating carbanionic center. And that is why new bonds are going to be formed. So this is a continuous process until we get to the point where there's no other bond to break. And that is where we have structure 1, 2, and 3 as the resonance or canonical forms. And structure 4 is a hybrid. If you look at the hybrid, you realize that the dotted starts from covered where all the positive centers are, meaning that in resonance hybrid, this positive center is being dispersed round the ring. That is why it is more stable than the canonical or resonance forms. After the slow stage, which is attack of the electrophilic species, we are going to have a fast stage, which is where our catalyst is being regenerated. So in that case, the catalyst that is not complete is going to come and react and take that hydrogen that is there in the system to stabilize itself and become regenerated at the end of the reaction. In nitration of benzene, the first stage is using the reagent to generate our electrophile, which is NO2+. In nitration, the reagent is conc nitric acid and conc sulfuric acid. Remember, they both must be conc. This conc nitric and conc sulfuric are going to help us to generate the electrophile, which is NO2+. And the catalyst is no more complete. So that is what happened in the first stage, where this catalyst is going to come again to react, so as to take hydrogen that is going to be eliminated from the reaction to make itself regenerated. So the first stage is generation of the electrophile. The second stage is attack of the electrophile, which is a slow stage, before re-aromatization, where catalyst is being regenerated and the hydrogen is being eliminated from the ring. that happens in sulfonation of benzene. The same thing that happened, we are going to generate sulfonic acid, which is HSO3. We are going to generate it and using the 2-sulfuric acid to generate it. At the end of that, just like also regenerate the catalyst, which is sulfuric acid. In halogenation, a typical example here is bromination. We are going to use iron 3 bromide to generate our electrophile, which is bromine cation. So at the end, the same protocol that happened in others was also. The crafts are two types, alkylation and acylation. In alkylation, we are adding alkyl to benzene ring. It means that the hydrogen that we are going to substitute or replace it with alkyl. And this alkyl is going to come from alkyl chloride under the presence of Lewis acid to generate an alkyl cation. But there are limitations. The limitation is that aryl halide and vinylic halide cannot be used because they cannot form carbocations easily. And there is always poor yield when there are electron withdrawing substituents like NO2 or amine that are being attached to the ring. Another limitation of Friedecraft is polyalkylation, which occurs when primary alkyl halides are used. We end up having polyalkylation, which is more reactive than the starting material. In Friedecraft acylation, we are going to use acyl chloride to generate our acylium ion. Acylium ion, just like we did in alkylation, is going to replace the hydrogen we are substituting from benzene. Now, in this case, remember we are forming a ketone, and some mistake students make is forming the bonding from oxygen. With oxygen don't bond, because if oxygen is bonding, the valency of carbon cannot be maintained. So in forming ketone, it is carbon that bonds with carbon. Remember the place where hydrogen left, we are having carbon there and negative center. So that carbon is going to bond with that carbon before oxygen and alkyl follow suit to form a ketone compound. Now, types different between alkylation and acylation is that in alkylation we form alkyl benzene, but in acylation we are forming ketone. But something that's similar between them is that they are making use of the same Lewis acid, which is aluminum trichloride. Effect of substituent on benzene ring. Methyl benzene, which is toluene, react faster than benzene. Why? The reason is because methyl has electron donating potential, hence activates the ring. All activators are autoparadirectors, and making that any actin that activates hastens the reaction, makes the reaction occur faster. So toluene in nitration reacts faster than benzene in nitration. So if a question is asked about which of the following compound is more reactive, look at the substituent. If the substituent on the benzene ring is activators, it means that it's going to be faster, more reactive than the one that are deactivators. Activators are autoparadirectors, and they make the reaction occur faster. So toluene is going to react faster than benzene. So this reaction, because of toluene, is faster than a one that does not have methyl attached to it. Now, when I have nitro compound attached to benzene, forming nitrobenzene, because of this nitro group is a electron withdrawing substituent, they are going to deactivate the ring. When somebody collects things from you, nobody is happy paying. We are always happy collecting. That's when whenever alert comes and it's credit, you smile. When alert comes and is debit, you are not happy, just like but whenever there is credit alert, so that credit alert is activators. They are donating to you, is addition to you. But whenever there is debit alert, they are taking it from you, so you're not happy. So deactivators are electron withdrawing, and they make reaction to occur slower, while activators make reaction to occur faster. So when I have NO2 in a ring, the reaction is going to be slower than that of normal benzene ring, while activators are going to be faster than benzene ring that does not have any substituents. Activators are method directors, while deactivators are method directors, while activators are auto-para directing. Activators and deactivators. Under activators, we have strong activators, moderate activators, and weak activators, but they are all auto-para directing. Under deactivators, we have two types of deactivators. We have method directing, which is NO2, cyanide, carboxyl, ester, sulfonic aldehyde ketone, and tertiary amine. They are all deactivators. It means that when I have them as substituent on benzene ring, any other incoming substituent, they are going to push them to meta position, position 3. But when I have activators, like I have a phenol, if I want to nitrate phenol, any other that NO2 will be auto-para, because phenol is the leader, and phenol are activators. And because of phenol, because of hydroxy group, that benzene ring is going to react faster in nitrating the compound. But there's something that is unique. These are halogens. Halogens are deactivators, yet auto-para directing, because they are strongly by inductive effect, and also they have resonance. Because of that resonance, being able to donate lone pair of electron and stabilize by resonance, they can also be auto-para directors. Looking at this, the group attached can either increase or decrease electron density. When methyl is donating, there is increase in electron density. When chlorine is taken, there is decrease in electron density. So withdrawing is decrease, while donating is increase in electron density. When there is increase in electron density, the reaction occurs faster. When there is decrease, the reaction occurs slower. And taking from that system make that system much more acidic, while releasing make the system much more basic. The group attached interact with the electronic structure of the ring in such a way that will give either auto-para position, acquiring positive or negative charge, and this can be understood easily when we are talking about resonance. Amine, that is aniline as a compound, because there is lone pair of electron on nitrogen, they can interact with the ring with unsaturated nature of the ring. Now, the places you're going to see negative centers, which is carbanionic center or nucleophilic center, these are auto-para position. So that is why they are auto-para directing, because this negative center is where your electrophilic species will come and attack. So they can attack in position 1, they can attack in position 2, in position 4, or the other side of position 2. So that is why they are auto-para directing. Remember, position 2 and position 6 are similar, so they can be called position 2 depending on where you're coming from, but it's better to call them position 2. So that's why these are auto-para directors, by virtue of this interaction in electronic structure. About NO2, nitrobenzene, unlike what happened in aniline, nitrobenzene is giving us positive center in a place where we are having negative center in aniline. Remember, we are talking about electrophilic species. Positive center cannot come and attack in electrophilic species cannot come and attack at positive center. That is why auto, meta, and para is not available for electrophilic species in this nitrobenzene. The only place that can be available is meta position. So that is why NO2 and electron withdrawing substituents are meta directors, not autopara, and they are very slow. In terms of halogen, we can see that there is no lump of electron on halogen, and they can interact with the electronic structure of benzene by resonance, and that is why they can be auto-para-directing. If you look at that, you can see where our negative centers are in auto and para positions. So that is why halogens can be auto-para-directing, though they are deactivators because of their strong electron withdrawing potential via inductive effect. Hydroxyl and amino group, they have weak electron withdrawing inductive effect and strong electron donating effect, hence they are activators. While halogens have strong inductive effect and weak resonance effect. That's why they are deactivators but autopara directors. The substituents and their effects. Methyl are activators, hydroxyl amino are activators, halogens are deactivators, tertiary amine are deactivators. NO2, cyanide, aldehyde, and ketone, carboxylic functional group, they are all deactivators. So, apart tertiary amine and methyl don't have any resonance. So others have resonance. Hydroxyl amine and secondary amine is going to have strong electron donating by resonance, weak electron withdrawing by inductive effects. So halogen are the only one that have strong withdrawing by inductive effect plus tertiary amine. So anyone that have strong withdrawing are deactivators because any substituent that withdraw deactivates the ring. So anyone that have strong electron donating are activators, as seen on the table, except methyl that are weak electron donating by inductive effect. The addition reactions in benzene. Remember, benzene resists addition reaction. The reason is what you're going to see. It undergoes halogenation using platinum as a catalyst at a very high temperature because it needs this high temperature for the reaction to occur. This benzene will cease to be benzene, will become cyclohexane. So that's why benzene resists addition reaction of halogenation. Reaction of halogenation. Why benzene resists that is because this can occur under UV light, so it's a free radical mechanism, but it's going to take away every unsaturated nature of benzene. Benzene become cyclohexane again, but this one is going to have 6 halogen, so it becomes hexachloro cyclohexane, making it to lose its aromatic nature. And benzene resists anything that will make it to lose its aromatic nature because from unsaturation, addition reaction is going to make benzene to become saturated hydrocarbon. In terms of reaction with ozone, when benzene reacts with ozone, what happens is going to form an oxonide, and under hydrolysis it is going to form a 10-diol. This also disrupts the nature of benzene. From this is that benzene compound cannot undergo reaction typical of unsaturated like alkane and alkyne because of its aromatic nature will be destroyed when such addition reaction is being undergone by benzene. So benzene will prefer to undergo electrophilic aromatic substitution reaction in order to preserve its aromatic nature. Don't allow yourself to be intimidated. Take your time, follow your pace. Go through this slide all over and all over again so as to understand it more. Just like the way you sing some songs without reading the lyrics because you listen to them several times. So the essence of this recording is to give you opportunity to listen. So you can listen when you're traveling your phone, you can use your earpiece and listen. You're still doing lecture, you're still studying even when you are on the road. So that with this, you'll be conversant with everything that has to do with these topics. And when you enter exam hall, there will not be stress for you. Till I see you in the next class, don't live life alone. Remember, there is always somebody you can talk to make things work out for you. I wish you success in your career as a student, especially in organic chemistry. Thank you.